Content of week 8 is multiple integrals. So integration, just as before, only know of functions that depend on more than one variable. For example, a function in two variables, x and y, that gives a value z. So a function with domain in R2 and image R. We can still plot the graph of this function since altogether we have 3 dimensions. What should the integral of such a function be? Well, should not be different than in the one-dimensional case beforehand, where we had one variable and get a one-dimensional output. There we had the area with sign under the graph. So here we are expecting to get the volume under the graph. The concept is exactly the same as before. We make some Riemannian sums and then go in the limit to very, very small volume pieces to get the whole integral. So what are our pieces here that we're adding up? These are these cuboids as one is drawn there. These are the dv's, the volume elements, and they are given by the base from dA, which is a tiny little bit along the x-axis, dx, times a tiny little bit along the y-axis, dy, times the function value somewhere in this dA region. To decompose the domain into many little pieces, here for a rectangular domain we choose a partition in x direction for the interval a to b and a partition of the interval c to d in y direction. And then if we add all of this up, this is this double sum that you see on the right, you get the volume. So all these little cuboid volumes are functional value times dA, and dA is delta xi times delta yj. If now we take the limit, so if our partition becomes very, very fine and we have infinitely many little area pieces, then in the limit we get the integral. That is the integral from a to b in x direction, and over that the integral c to d in y direction. Again, you're replacing the sum by the integral if you go to the limit. The two integrals that sum up the addition in the x and the addition in the y direction are written as one integral. If we write over the whole domain, then we know that in this case it's two-dimensional, and dA is our area element, which is the dx times dy, where we are varying over both x and y to get the whole rectangle. This notation of one integral inside another integral can also interpret it again as computing slabs and adding them up, just as in week 7. Only here we can do it in general now. We are not restricted to slabs where we do know the area because of some reason like rotational symmetry. So look at the inner integral from a to b of f of xy dx. That is an integral that only sums up x values. So here the y value is fixed, and that integral gives us the area of a slab parallel to the xz plane. So for each y value we compute the area of the intersecting surface, and then afterwards we take the integral of the function that gives the area of these 0,6 slabs along the y-axis. That is the integral from c to d, a of y dy, where a of y is the integral we already computed. Of course, we can also do this the other way around. So first computing the areas of the planes that intersect the volume parallel to the yz axis. So that means that we first keep x fixed and compute an area that depends on this x value, and then afterwards we sum up all these areas along the x-axis. So in that case the inner integral is the integral from c to d f of xy dy, where now the variable is y and x is fixed, and afterwards we integrate over x, so we take the integral from a to b over the areas that depend on x dx. Now we have in principle the theory, so let's do an example. I would like to compute the integral over the function x plus y over the rectangular domain where the x values are between 1 and 4 and the y values are between 2 and 3. So this is the volume of the solid that would be cut out by this plane and that has the rectangular xy domain as base. We have the double integral where the function is the x plus y and the dA is dy times dx. dy is in the inner integral, so that is the one with boundaries from 2 to 3. And x runs from 1 to 4, so these are the boundaries from the outer integral. Next step, we're computing the inner integral. Remember, x here is fixed and y is a variable, so x is a constant, and x integrated for y is just x times y. Y integrated is a half y square. The boundaries are 2 and 3. We write these out and have an integral that has no variable y any longer. Well, it shouldn't. And we now have that the area of each slab parallel to the YZ plane has area x plus 5/2 that intersects the x-axis at x. Adding all of these up from 1 to 4, it's nothing else than computing this integral. We get a half x squared plus 5/2 x with the boundaries x equal 1 and x equal 4. Plugging that in, we get 15. That means the volume of the object with base rectangle D and height x plus 1 is 15. That's basically it. If the domain D is not a rectangle, as in the sketch that I drew here, we can still compute our integral of the function over the domain. Of course, somehow we have to get our hands on the domain, so it has to be given as either an inequality of the x and y coordinates that, for example, they're all smaller than a given distance from the origin if it's a disk, or we somehow need to have the boundary as a function. Let's say here we first want to compute the area of the slabs parallel to the YZ plane. Then we have to know from where to where we should integrate the y values. So the boundaries of the y integral, c and d, will depend on our x values. That means we need the boundary of d to be given as two functions, one c of x and one d of x. If we have that, we can write just as before the integral as a double integral, where the inner one gives the area of the slabs. So here from c of x now to d of x, the function dy, and then the whole thing integrated from a to b, where a and b is the minimum and the maximum point where the domain has the x coordinate. So the boundary function goes into the inner integral. Again, of course, we can change the order of our variables and first integrate over y. So first look at slabs parallel to the xz plane. Then we need our domain to be given as two functions, a of y and b of y, for the boundaries of the integral that is first in x direction. Unfortunately, I used a non-erasable pen for the slabs I drew beforehand. So here this is about the red stuff. As before, you see that the integral with the boundaries that depend on the last variable are in the inner integral. So we integrate x first from a to b, where a and b depend on the point where we cut the solid. And then afterwards we integrate all of these areas of the slabs from c to d, where now c and d are not dependent on anything but the smallest and largest y value that the domain has. Let's do an example for a domain that is not a rectangle. So here a disk of radius r around the origin, and the function we're integrating over it is constantly 1. And that gives us an interesting special case and application of these multiple integrals, namely, if we multiply over the function that's constantly 1, we get the area of the domain, because what we're actually computing is the volume, domain times 1 everywhere. So we get the area of the domain. That means we have a different way here of computing the area of a disk. Here's the computation for that. More that we see how it works in general than that you actually have to use all these functions, because actually it looks horrible in Cartesian coordinates, and it's a motivation for use different coordinates. In this case, polar coordinates would be the right thing, but this is not for this week. So here the boundary is given as x squared plus y squared is r squared. So this is the function that defines the circle of radius r around the origin. Now, if we first want to compute the slabs from minus r to r as in the picture parallel to the YZ plane, we first integrate over y and then we integrate all of that over x. So first we need to have the boundaries in y directions, and these should depend on x. We solve the equation of the boundary for y, and we get y equal plus minus square root of r square minus x square. This is two values, this is correct. The minus value is the one where we start integrating, and the plus value is the one where we end. The function is 1, and we integrate from minus the square root to plus the square root in y direction, and then the whole thing is added up from minus r to r in the x direction. Computing the integral of 1 is y, yippee-doo. Plugging in the boundaries, we get 2 square root of r square minus x square, and now this only depends on x, and we have to take the integral over this new function. So now this is a bit horrible, and you don't need to know that by heart, but it happens to be the function that is written below with the arcsine. Arcsine is the inverse function of sine, where the domain is the maximum domain that contains 0. Using that, when we plug in the boundaries, we get r times 0, okay, plus r square arcsine of 1. And what is arcsine of 1? That is p half. This is a good reminder for trigonometric functions. So why is that p half? At which value is the sine function 1? Well, the sine function is 1 in the domain that is closest to 0 at p half. So if we do it backwards, which we have to do because the arcsine is the inverse function, we get p half. And same for arcsine of 0, at which point gives the sine 0, well, at 0, so arcsine of 0 is 0. And then we get 2 pi half r square, and that is pi r square as we know. If we do everything with integrating over x first and then afterwards over y, this is nothing else than a change of coordinates. So you replace x and y in the calculation everywhere. This is not surprising since the disk around the origin is completely symmetric for x and y direction. In general, it's not always the case that it's the same computation whether you use x or y first. It can really make a huge difference also in terms of the function that defines you the boundary of your domain, whether you write it as a function y of x or a function x of y. In general, one can be really easy and the other way horrible. One has to be a little bit careful. Here, example 2 from page 824 is worked out. So evaluate the integral of the function xy, where the domain is the triangle with the vertices 0, 0, 1, 0, and 1, 1 as in the picture below. So if we first want to integrate over y and then over x, that means we need to have the boundaries of y first for each interval over x. The first value is always 0, so that is easy. And the end of the interval is given by the function y equal x. So in the inner integral, we write from 0 to x dy with the function xy in the middle. And the outer integral is from 0 to 1 over x. Solving that is very easy and straightforward, and doing it with changed variables, so first integrating over x and then integrating over y, means that now we have to give the intervals for x independency of the y vector, and we write it in the middle integral. So here the left side of the integration interval changes, again with the function y equal x, so it starts at y, and we end up at 1 always, so we write y to 1 of xy dx, and the whole thing is then integrated from 0 to y equal 1, and gives the same integral as it should, equal 1/8. Both important for understanding but also useful for computations is it to know some properties of integrals. So for multiple integrals, that's not much different from one variable integrals. First, if our domain has 0 area, then the integral is also 0. Well, that's not really surprising. If I only have one value over one point, then its volume is the function value times 0, well, and that's 0. Second property we had already. If we integrate over the constant function 1, we obtain the area of the domain. C. The integral over the function f of x integrated over the two-dimensional domain D is the volume under the function graph. Just as before in the one-dimensional case, if the function values are negative, so if the graph is below the z equals 0 xy plane, then the volume is counted negative. This is why I wrote with sign. In the book you have two properties there, where it once says it is the volume if the function is always positive, or it is negative the volume if the function is always negative. These are like special cases. In general, it just gives you the volume where everything that's below the xy plane intersecting z at point 0 is negatively counted, everything above it is positively counted, just as before. Integrals are linear functions. That means we can split sums and we can take factors out. If one function is always smaller equal than another function, then the integral of the smaller function will be smaller equal than the integral over the larger function. It is also pretty clear the volume under the graph of a function that is smaller should be smaller than the volume under the graph of a function that is bigger. G, this is a triangle inequality. If you put absolute values inside the integral, then the value is greater or equal. How does that come? Well, on the left hand side there could be negative values, and everything where the function values are negative is subtracted. If we first put everything above the xy plane, then the integral will stay the same or become more if we had any negative values. Pretty clear. H is about not adding up functions but adding up domains. If we integrate over a domain and we split it, then we can also just integrate over the first part of it plus the integration of the second part of it. So here of course it's important that we don't do any parts double, so the intersection of the two parts should be 0 and the overall domain should be made up from all the single parts we're integrating over. Triple integrals, chapter 14.5. So that's really just adding another integral into one more direction. So the same story, 3 variables. F takes x, y and z and gives us a real value. We want to do our Riemannian sums. The tiny cubes that we're adding up this time are actually 4-dimensional. They are the dv, which are the volumes of the domain in R3, times the function value. So 4-dimensional, what does it compute? Again, if we integrate over the function that is constantly 1, this gives us the volume of the domain, and that can be a useful way of computing a volume. In general, it's a 4-dimensional volume under the graph of f. Okay, when do I need a 4-dimensional volume? You actually have seen such a case. For example, if the function gives you the density of a material at the point x, y, z, then the integral over the domain, where the domain is given by all those points where your object is, over the density is the mass of the solid in the spatial region D. This is example 3 on page 845 in chapter 14.5. And we are asked to find the mass of the tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0 and 0, 0, 1, whose density is given by the function that assigns to each point the y coordinate. So that's so easy that we could even do it with the tools that we had beforehand. And if you want to have it a little bit more complicated, choose a different density function like x plus y plus z, or 2x plus y squared plus a certain z. The calculation is the same, only you have much longer terms under your integrals. And with such a function you cannot do it any longer with the tools that we had beforehand, computing the slabs and using only one integral. Anyways, so now we need to know the formula for the boundary. So here the upper face is given by z coordinate is 1 minus x minus y. The diagonal edge in the xy plane is given by y equals 1 minus x. And all the other coordinates are easily read off. One face is given by y equals 0, one face is given by z equals 0, and the last remaining face is given by, what is missing? X, y and z once each is 0. Then to get the mass we integrate over the density and the volume. So writing this as triple integral using the formula for the boundary. First we go up in z direction for each point xy. This is the length of the red line. Then we go in y direction, adding up all the lengths of the red y lines in one triangle face that is parallel to the zy plane as the t of x drawn in the figure. And then finally in x direction we add all of these triangles up. So the inner integral goes from the xy plane, so it starts at 0 to the z coordinate, which is 1 minus x minus y. y is the density in the integral, dz. Then the second integral for y, we integrate from 0 to the diagonal line in the xy plane, so this is 1 minus x dy, and finally dx from 0 to 1. That was most of the work. Now we can calculate one of the integrals after the other. In the book you sometimes see the dy and the dx behind this first and second integral. That is perfectly fine to write it like that. Depends a bit on your taste, so I prefer to think an onion where I start from the inner peel and then the middle and the outer peel, but both is fine. The rest is straightforward computation 3 times taking an integral, only being careful to know which is a variable each time we're integrating over. So the first one is z, so y is a constant in this case, and the antiderivative of y, if the variable is that, is yz. That's the first step. Plugging in the two boundaries of the red lines, which was 0 and 1 minus x minus y, we get the next integral. And now our variable for integration is y, so x is a constant. We got rid of all the z's, so now there really shouldn't be anything dependent on z any longer. Computing the antiderivative of y minus xy minus y squared, we get the fourth integral on this page. This describes the area of each of the triangles, and we have to integrate over x finally to add up all the triangles from 0 to 1. And that gives us 1/24 finally as the mass of this tetrahedron. It was kind of natural to start with the z coordinate and then integrate over the y and finally over the x coordinate, because this is how our boundaries were given. One function in x and y, one function in x. But of course you can also rearrange it and integrate with a different order of the coordinates, then your functions will also be different. If you want to do that, this can be a good exercise, and you can compare with the book where all the different options are written out with the changed boundaries. Now we are pretty much done with integration. We'll only come back to it when we do coordinate transformations to compute integrals using different coordinates.